I'm in this folder, how do I accidentally do our folders on my computer? Oh, no. I can't forget. Yeah, that's accurate. Dr. Ing,
Yep.
I have a question about the homework. So
Okay.
the last question, based on the height, were those guys actually from the Netherlands? Because I don't think that my t-test said that they were. It said that they were outside.
They're statistically different from the Netherlands, right? Pretty sure it said that.
That's what mine got. So,
Anything you mentioned that.
Because their mean was only like, what, 4 centimeters different?
yeah, and the standard deviation was 5.1, so I thought like maybe they would be.
Yeah, that's a question that I have about t-tests in general is, like, why can't you just look at the standard deviation, and if they're outside that range, they're not normal? Isn't that
Not just a confidence interval.
So why can't you just look at standard deviations? Because standard deviations are gonna be affected by our sample sizes, and we would have to look at our standard errors to do that. And if you did 2 times the standard errors, then you could approximate a 95% confidence interval, but only if our vector is normally distributed.
okay?
Only if it's normally
So
distributed.
it has to be normal, and the sample size for the sample size.
So you have
be
to
large
take
enough.
your standard deviation and make it a standard error. You have to convert it to a standard error, and that's why I don't make a big deal about doing this 2 times the standard error, because I saw that people were trying to take. I would ask the question on a final exam that says, "Is this mean equal to some value? Is the sample mean equal to some value?" And they took the shortcut of 2 times the standard error. But I can actually manipulate it, because if you're not normally distributed, then I can make it fall outside or fall inside the range when, in fact, it's not.
Interesting.
So I've avoided talking about that. It's a quick and dirty way to kind of look at it.
Yeah.
I would do it if I was in the field and just kind of eyeballing it and I was curious, but no, you have to do the stats. So speaking of homework, right in the homework, I have the keys part. So normally, and under a normal year, these would have been posted outside my office, and I would have required you to come and look at them. And if you wanted them, take copies or sit down and transfer onto yours. But these are the PDFs of the keys for our various homework assignments, so all the way up through 9. So I posted number 8 and number 9 today. It is your responsibility to compare my key to your key, or to your homework. All right, see how, if you got the same answers, same conclusions. In some cases, I add a little bit more information on the key. Some maybe some explanation as to why I did it one way or the other. But check it out. I will do those.
Government issued IDs. I like that right up.
Nothing.
I added a little bit of clarity. And I also have the exam keys. So I don't know if you noticed that. I also posted exam 1 and exam 2 keys. These were the application parts, because you should be able to go to the exams themselves and view your answers and see what you got wrong. So you would go to my grades and so forth.
Is your final cumulative?
It is.
Okay.
Final is cumulative. So yeah, some of the final is the application part is I will tell you to run the appropriate test. So make a QQ plot to answer this question, or run a t-test to answer this question. There are a couple questions though where I say, here's the data, run through all your process and choosing the correct steps along the way. That's kind of like the big, did you really kind of leave this class understanding, or at least having an idea of our flow of what we do. And I do have, after we do like the introduction to ANOVA and we assume that all of our assumptions are met, I do kind of take a break and we kind of step back and start from the beginning and say, okay, we've collected data. This is what we look at. If we have this, these are our options. If we have that, these are our options, and so forth. So we kind of build a flow chart that would help us figure out what tests to run or what our options are.
It's gonna be in those two parts. The final is gonna be in the two parts. Like all the other ones.
Yep. So yeah, the final's in the two parts. Our final is scheduled for Monday, and I believe the syllabus had a time when we were going to take it,
I
maybe
didn't
like
check that.
10:30 to 12:30 or something like that.
Make sure it was.
That was written at a time where I had thought that face-to-face meant face-to-face, wasn't virtual. So ignore the time part. On that Monday is when you will have to do the closed book portion. The application part, I will probably make it go live on Friday, and then it'll have to be turned in by the end of Monday. So you'll have some time to kind of do it and get it done ahead of time. All right. So t-test, 2 groups. Just quick review. We measured variable, the measurement variable, all right, and we measured this variable for 2 groups, 2 different groups. All right, and we're interested in if that measurement variable is different between groups, or perhaps maybe if the groups themselves have an effect on that measurement variable. So our statistical question is that the means are equal. And the way we go about doing this is if they're equal, then the difference of the means is equal to 0. And that allows us then, going the wrong way, to do this transformation. So our regular t was, if you remember, our regular t observed was this x minus the mu over our standard error. That was our t. And we did that for the homework whose key just went live. So we had our t is x minus x mu. All right. If we think that our means are equal, so if our hypothesis is that x bar 1 is equal to x bar 2, x bar 1 is equal to x bar 2, then we can change our hypothesis to say that the difference of these is equal to 0. And when we do that, then this term x becomes x bar 1 minus x bar 2, and our mu becomes a 0. And we still have a standard error to contend with. All right, we still have a standard error to contend with, and that's what I have up here. So that is the whole idea behind a 2-sample t-test, is that we're testing if the difference in our means is equal to 0. If it's equal to 0, then we know the means are equal. If it's not equal to 0, then we know the means are different. All right? So if we did it by hand, we have to do this. We have to calculate the t. Our degrees of freedom is our sample sizes. The sum of our sample size is minus 2. So our sample size minus 1, and then add it together. Right? And we said that our assumptions, data are random and independent. Data are normally distributed within each group, and variances of the group are equal. We will return to these assumptions. For now, we will assume that all of our assumptions are met. So, posted, I have t-test example.csv. So, download it off the Blackboard, read it into read it into R, and call it EX1. EX1 for example 1. Alright, so I'm going to start up my R markdown, or my studio. Probably have this. Alright. Should read it in. Still reading, probably. Access denied. This is just annoying. All right. Did you get it? What presentation? Word output. So, let me get this going. Here's my R markdown. Started to create it. So at the start, I'm going to have my data. I'm going to have a library section. And possibly we'll have a function section. Right. So you use input, import data set, going to read it, ex1. I can see that I have two variables. I have test and I have height. All right. I can see my test is a factor with two levels, and my height looks to be continuous. Looks to be some sort of measurement variable. All right. That's what it looks like. So, move this out of the way. So what is this data set? What does this represent? This data set represents a situation where we measure the height of plants at the end of an experiment. All right? And our experiment that we ran had two different test conditions. I think it called it test A and test B, maybe. All right, so our question that we're asking is, does the heights differ between our tests? Or does the test itself, test conditions, have an effect on our height? The statistical question then is that our mean of test A is equal to the mean of test B. And then our alternate is that they're unequal. So is this a one-tailed or a two-tailed test? One-tailed or two-tailed? Two-tailed. All right, so it's either equal or it's not. And this is going to be the case kind of moving forward. So this is our statistical hypotheses. We have two variables. We have a measurement variable, and that's our dependent variable, and our second variable is a categorical variable. It's our independent variable. That gives me the options to say, okay, well, we're going to run something like an ANOVA, and that categorical group is only two levels, test A and test B, so we can run either an ANOVA or a t-test if our assumptions are met. What are our assumptions? Data are random and independent. We'll assume that's true. Our data are normally distributed within each group. This means that for test A, all of the heights are normally distributed. For test B, all of the heights are normally distributed. That's what that assumption means. It's not that all of the heights are normally distributed. It's normally distributed within each of our groups. We're going to assume that's true. And then second, our final assumption is that the variances of heights for each of our groups is equal. All right, we're gonna assume that that's true. So if all of these are true, then what we're gonna run is a t-test. How do we run a t-test? Well, using the function t.test. T.test. And this is how we're going to set it up right here. We're gonna set it up as an equation, as a formula. So think back to what you've learned about as an equation for a line. If I asked you, what is the equation for a line, what would you tell me? What's that? Y equals mx plus b. Exactly, right? If you go back to algebra and you talk about equations and solving for x, it was always like f of x equals some equation, right? We do it the same way here, where we're going to write it as y, our dependent variable, the x, the f of x value, is a function of x. So y squiggly x. So we're saying y, our dependent variable, is being represented as a function of x. All right, where do we get the squiggly? I guess you can say the tilde sign. Tilde. What's that?
Yes, tilde.
Tilde. Tilde. Tilde.
It's the thing over in India.
Or probably it's like tile. Tile.
I have no idea.
I don't know. But it is, if you look at the keyboard, it is above the accent mark. So you have to use the shift key to get to it. All right, so that's going to be our squiggly. This sets up a formula. And we're going to be using these formulas, or the formula format, many more times, not just on a t-test. All right? So when we do it this way, when we set up this formula like this, we don't have to use the $sign function. We give it the variable names because the second option here is for us to specify the data frame. All right? So we would do our variable y, our dependent variable, as a function of our independent variable, comma, data equals our data frame name, all right? And then var dot equal equals t, all right? So this var dot equal tells R, assume that we have equal variances, all right? If we don't, if that's the only assumption that we violated, we're going to learn we can set this to false. And I'm going to recommend that we actually do that, set it to false when we violate the assumption. But for now, we're going to assume that variances are equal, so var dot equal equals t. All right? So, that next slide. Let's take a look at our data set. Let's learn about some other things in R. So we know the heights. It's over. Put her on wheels, but they don't let us feel it. Like, it'd be so much better if we were like angled this way. Oops and stuff. So I can get to my keyboard a little easier. All right. So we read in our data set. Example 1. We grew plants. We grew plants under 2 different conditions. That's what we did. Are the final plant heights different? That's what we're interested in. It's just like let's say a master's thesis question. Are the heights different? All right. So based on that, we're going to have our null hypothesis is that our x bar I guess we'll do it like this. Bar x of group A is equal to bar x of group B. So, you know, it's our x bar values. And I'm not sure what that is for our, you know, $sign backslash, which one that is. But that's our null hypothesis. And then our alternate hypothesis is that they're not equal. All right. We're going to do a two-tailed test. And then if we reject this claim, then we can kind of go back and look at our averages and say which group is taller than the other. All right, so this is our $/NEQ $. And that's not equal, right? It's not equal to it. I found out today LEQ is less than or equal to sign. And then I would then assume that GEQ is the greater than or equal to sign. I would assume. I didn't try it, but I know the LEQ is. All right, so first thing we want to do with our data set. Let's look at our data first. We did our experiment. Let's look at our data. First thing we want to do is let's look at the average height of our data. Average height for each group. All right? We're going to use a function called the aggregate function. All right? We're going to use this aggregate function. We're going to set up our aggregate function as a formula, just like we would do for our t-test, all right? Where our dependent variable is the y, we're going to use the squiggly, and then our independent variable is the x, all right? Since we write it as a formula, we're going to give it the data frame, where it's at, and then we're going to give it something called fun, which is the function. All right? So, it's where y is the dependent measurement variable, x is the categorical independent variable, data equals data frame, specifies where to find the variables, and fun is the function. Okay? Aggregate will apply the function fun that we give it, to the y variable for each level of x. All right? That's kind of the verbalization of the aggregate function. Now, there's some other functions that will accomplish the same thing. I like using the aggregate function. This is what you'll see me use. I think it applies in many more ways than some of the other things that we could have used. All right? So, here's how to calculate the mean of height for each test group. All right, so we kind of laid it out what we're going to be doing. We're going to use our aggregate function for this. So aggregate, height as a function of test, data is EX1, that's where we find it. And then fun equals mean. So again, this fun, it's got to be all capital, F-U-N, equals, and we have to give it a function that is built into R. Okay? And then, when you run it, you will get this output. This gives a pretty nice output. In our markdown, it gives us this table. So we can see that the height of test A is 25.344. The height of test B is 26.658. 26.658. Okay. So our question is, are these means the same? We know that they are different, and if we were to repeat the experiment, we'd get slightly different numbers. All right. But if they were different, if the means are actually different, then we would see the same pattern. We get slightly different numbers, but B would be larger than A, and so forth. All right. So what else can we do? Well, I'm going to open up my functions. And let's say we wanted to make a figure, right? I'm going to run the standard error. So with our figure, R makes okay figures. The defaults are box plots. You can make really nice figures, but you have to kind of delve into making these things by hand and manually drawing, telling R the code to manually draw like our mean lines and our error bars and so forth. And if you need to do that, come talk to me. I'll help you out. All right. But the easiest way to make figures, at least for presentations and posters and stuff, is to take the data from R and make it in Excel. Because you're probably used to making things in Excel. So here's our means. So we'll do our standard errors. Error bars in Excel. All right. Uses the same thing. Aggregate height as a function of test. Data equals ex1. Fun is sterr because that's what we created. We created our own functions so that we can do this. We can use it in our aggregate function. So now we have our standard errors. And remember that bs.mean function? It can be used with this. There's been reasons why I created those functions. It's for use in our aggregate function. As we start adding an independent variable that has more than one group, this is why. Aggregate needs those functions. All right, so right now we look at this. We can take these to make a figure, or we can do it in R. So the basic functions plot, and we report it, we do it in much the same way as any other formula. So we write it as, we want a plot of height as a function of our test variable, where our data is ex1. And when you run it, you'll see we will get a box and whiskers plot, which is okay. But normally we're interested in comparing means and not medians. And this tells us, the box plot shows the medians. That's what those show. Now what we'll do in this class, a lot of times we will make these box plots just to kind of get an idea of, should we expect a difference or should we not expect a difference? So looking at our aggregate function, we see these values. Does it suggest, do these means suggest that our means are different? I don't know. We have to kind of look at our standard errors. We can do an approximation, kind of think about it in our head, or we can do a box and whiskers plot. Look at it. What do you say? Does it look like our medians would be different? And remember, if we're normally distributed, then our mean and our medians would be equal, or pretty darn close to equal. So what do you say?
I'm trying to remember, is the white box around the median, is that the 25 to 75?
Yep, that's the, yep. The box itself represents the interquartile range.
Okay.
And then those whiskers are the maximum value or 1.5 times the interquartile range.
Isn't that also a confidence interval, or is that just?
Well, if it's minimum and maximum values, that represents the range.
Okay.
But for our dispersion values, if we're reporting medians, we would report interquartile ranges. So just based on this figure, what do you think? Should we expect our heights to differ between our tests?
I think yes, because the medians aren't really within each other's IQRs.
Okay. So good rationale, medians don't seem to fall within the interquartile ranges of the other groups. So that median is outside of this one. This median's just outside of that one. So if I asked you, what would the p-value of approximately, what would be the p-value? Give me an estimate.
If they're different, would the p-value be less than 0.05?
Okay,
We
so
don't have that back.
you say if they're different, it will be less than 0.05.
That would be our
What?
expectation.
Give me a better estimate. Not only less than 0.05, what value? Okay,
Is that gettable from looking at the box and what's required?
I'm sure it is.
as you guys think about that, I had a question because we have a plot, gives me an error saying that it can't find xlim. Drop down this box. Do you see the same information here? Because my guess is no. That when you read it in, when you did your import data set, go to here, click on it. Documents, ASU, biostats, R data. This is a t-test data. T-test example, I guess. Heading equals yes. So when you import it, you need to see these variables up here. So if you didn't, then you would get V1, V2, and when R looks for our groups, or actually when it looks for our Y variable, it sees height and assumes that this thing is a text variable instead of a continuous variable, and it gets really confused. So read it in, just make sure that heading is clicked for yes, and when you read it, you'll actually have the variable names here, test and height. All right, now that we've had time to contemplate, what p-values? Give me just the best guess.
0.045.
0.045. Do you agree?
Seems reasonable.
Okay. Okay, so I've told you. I've told you that the p-values, we set cutoff 0.05, right? If it's less than 0.05 or equal to or less than 0.05, we reject our null hypothesis. If it's greater than 0.05, we fail to reject it, right? And I've said that the value of the p-value doesn't tell us anything about being more significant or less significant. And that's true. But when we look at a graph like this, you can see, well, maybe there's not going to be a difference. I think Cody had it right with saying the medians are not in our interquartile ranges. So he does think it's going to be significant, but our p-value is going to be closer to 0.05 than not. We're not going to get a p-value that's 0.000001 or what, 2.26 e to the negative 16.
Yeah.
All right, that's way too small. If none of these overlapped, then I wouldn't be surprised to get a really small p-value. But we're going to see, we're not going to be surprised if our p-values say between 0.01 and let's say 0.1, where it's kind of in that range where maybe it's different, maybe it's not different, maybe we don't have enough power to detect it. So, yep, so Nate says about 0.035 or so. Yeah, it's close. It's significant, but close. All right, so we based it on it. Now let's check, and we kind of have a prediction as to what we expect based on the view. And this is always what we want to do. We always want to look at it and kind of form an opinion so we're not surprised. Like if I get a p-value 2.26 e to the negative 16, I'm going to say something must not be right here. All right. If I get a p-value of 1, something's not right here. So let's run a t-test. All right, so we already have the code. It's as simple as saying t.test and writing the formula that we've been using for both the aggregate function and our plot function. So height as a function of test, data equals ex1, and var.equal equals t. I believe the default is that var.equal equals t. I believe that's the default. So when we run it, we get this. All right, So with our tests, we're going to see the output. The output tells us what test was run. This was a two-sample t-test. All right. It didn't say anything about equal variances, and I'll show you what happens when we change this to f. All right. The data that we used was height by test. So we looked at height as a function of test. Our t observed value is negative 2.456. So again, going back to what we were doing, we're testing if the difference is equal to 0. No, our t observed is actually farther from 0. It's negative 2.456. The degrees of freedom, 48. Does that make sense? Yeah, I've had 50 observations. I had 50 rows. Our degrees of freedom for a two-sample t-test is that sample size, number of rows, minus 2. 50 minus 2 is 48, and we get our p-value, 0.01772. So it's not like super small, and it's not super large. It's what I would say is kind of close. It's within what, 0.05 of our 0.05. It's kind of in that region where we could do better, bigger sample size. Or we could do worse with the smaller sample size. All right, confidence interval. This 95% confidence interval is not the 95% confidence interval of the mean. That is the confidence interval of the difference of our means, because we're testing it against 0. So does this confidence interval capture 0? No. And remember, when we did our bootstrap confidence interval, we said if that interval captures our hypothesized mean, then there's no difference. If it doesn't capture that hypothesized mean, then there is a difference. Well, our 95% confidence interval does not capture the 0. So we know that our means, or this difference of our means, is not equal to 0. And then it also gives us a sample estimates, but we already had those. We already had those means. So based on this, we can go ahead and do our write-up. Right? We can do our write-up. So we asked, do the heights differ between our tests? And our conclusion? Yeah. Test conditions do have an effect on overall height of the planes. We ran a t-test. Our t is given in our output, negative 2.46. This is a case where we don't necessarily need to use a negative because it's a two-sample test and we don't set up direction, so we could just as easily switch A and B to get our positive. If you've done this by hand in another class, you would have used absolute values to make sure you're always working a positive. I would probably just use a positive for this. So we've got 2.46 degrees of freedom given in our output is 48, and our P is less than 0.02. So we have this conclusion or interpretation, test statistic, degrees of freedom, p-value. This one has all 5 items. Questions?
So when a t observed doesn't have to be a negative, does that mean we can switch test as a function of height, so we get the same p-value? No?
We did this.
Okay.
That's what it's doing, this x1 minus x2. If we reverse it and did x2 minus x1, we'd get our positive.
Okay.
That's what we mean. Try it. You can switch height and test. Try it. I don't think it'll work. So with this formula, we need our dependent variable to be that y, and then we need our grouping variable to be the x. because R will break it apart and say, okay, here's all of our test A's, here's our data, here's all of our test B's. It'll calculate the mean of both, calculate our T, and then use the PT function to get our mean values. It is just subtracting the means, and then divide by the standard errors. The standard error of our population. So, yeah. And the standard error of our population is basically a weighted standard deviation. So we do account for differences in sample size. All right. Questions? So in our presentation, here it is. I give the write-up, give everything. I did report the negative here again, but on a 2-sample test, all you have to do is change what order, which one is your X1 and which is your X2, and you can get the positive. All right. So we have everything. So practice, raspberry.csv. So we've counted the number of fruit produced by raspberry plants at the end of the growing season. We use Miracle-Gro as fertilizer for one row of plants. Then you use an organic homemade fertilizer for the second row of plants. Probably some essential oils. My wife was doing this. All right. Did fertilizer cause a difference in fruit production? I know she'll never watch this. I'm safe. All right, so raspberry.csv is in there. What I want you to do is download it, get it into R, look at the data, do everything that we've done, kind of get an idea of should I see a difference or should I expect to see a difference, approximate p-value and so forth. Then run your t-test and do a write-up, okay? What we will do is on Monday, we will pick this up. We will look at what you did, your interpretation, your write-up, and then we will move right into analysis of variance. I do say don't check your assumptions yet. We'll get to that. We'll introduce ANOVA because we can do ANOVAs on these as well, and ANOVA has the exact same assumptions. So with the ANOVA, we'll then show you how to do our tests, how to do our assumption checks. Yep.
So when you click down on the function for the vector of raspberry, it gives you fertilizer and fruit. Is that order the same orders like XY, like it was with EX1? So how test was X and height was Y, would fertilizer be X and fruit be Y?
Probably.
Okay.
Which one's your independent variable? So the question was, when you read in, let me read in raspberry. Go ahead with that. Let's do this. There it is. Copy that. Raspberry. Yeah, when I drop it down, it says it's got fertilizer and fruit. All right. So when you think about what is our X and what is our Y, think about what's the independent variable, what's the dependent variable. So here, what's the independent variable? Ooh, fertilizer.
Yeah,
Fertilizer.
Oh, wow, yeah, that would have worked.
Oh,
it would be.
Wait, how did that?
I misspelled.
Mine got
Fruit
saved
as a function of fertilizer, right?
Is it yours spelled correctly?
Yeah.
Let me download the corrected one. Let me download the corrected one. And fruit. So yeah, what's the independent variable?
The fertilizer.
It's our fertilizer.
Yeah.
All right. And our dependent variable is fruit because fruit might depend on what type of fertilizer we get. And is that always going to be the case? Open up Excel here. Yeah, in a blank workbook, when I record my data, I would probably have like date, all right, and then let's say pond, location, species. Let's say I'm measuring snails, shell height. All right. So how I get everything up is height's one variable, and that's the one variable that we measure, and it could depend on what pond we collected our individuals from, or the date in which we collected them, the location within the pond in which we collected them. So we break the pond down into, different areas, different coves maybe, and then the species of snail. So how you kind of set up your data set as you record data in your notebook, you typically set it up so all of these first columns are your X's. These are all your independent variables, and then your dependent variables end up being later on in the Excel spreadsheet. All right, so what we'll do on Monday is we'll look at this output. If you have questions, feel free to email. Yep, Jake was right. All right, have a good weekend.